So in this video, we'll be talking about problem number 5 from the 2021 AP Calc AB exam. They tell us we've got a function y equals f of x whose curve is given by this relation here for y being greater than 0. They ask us in part A to show that the derivative of y with respect to x is going to be equal to this fraction. Now, to take the derivative of this equation, you can just dive right in and take the derivative of both sides with respect to x. You are going to have to use implicit differentiation to have success with that. And when you use implicit differentiation, you're assuming that y is a function of x. So when you take the derivative of this term right here, you've got an outer function, 2 something squared, and then an inner function, y. And so when I take the derivative of the outside function but leave the inner function inside of it, I'd get 4y, and then when I multiply by the derivative of the inside function, I'm going to multiply by dy dx, the derivative of y with respect to x. The derivative of the 6 is going to be 0, so that's the only term that you see on the left side of the equal sign. And then when I do the derivative on the other side, if I'm assuming y is a function of x, I've got to look at y times sine of x as a product of two functions of x. So I've got a product rule being applied here, derivative of the first, original second, plus original first, derivative of the second. I want to solve for dy dx, so I'm going to group all of the terms that contain dy dx on the left side of the equation. I've already got this one on the left side of the equation, but I would like this term to join it. So to move that to the other side, I'm obviously going to have to subtract it. This guy here, y cosine of x, doesn't have a dy dx on it, just leave it be. And then if I factor dy dx out of the two terms that contain it on the left side of the equal sign, I'd end up looking at this, and if I want to isolate dy dx, I just divide by that set of parentheses, and I have now shown that the derivative of y with respect to x is that fraction that they started us out with. Part B asks us to write the equation of a tangent line, write an equation, not the equation, misspoke there, write an equation for the tangent line to the curve at the point 0, square root of 3. So even if you hadn't had any success with part A, this part of the problem should be pretty manageable. You're just going to evaluate the derivative, which they gave you the answer from part A. Evaluate the derivative at this x and this y. You don't have to do anything beyond this line right here. This would receive full credit. You know, if this was a multiple choice question, you definitely wouldn't be looking at what you see across my top line here. So I did do a little bit of simplification. Cosine of 0 is 1, sine of 0 is 0. I can cancel the square root of 3's. And then if I wanted to get a slope-intercept equation, which if it was a multiple choice question, could very well be what the options are formatted within, you're looking at y equals 1/4 x plus square root of 3. Part C says to find the coordinates of the point where the line tangent to the curve is horizontal. So the line tangent to the curve is horizontal if the slope of that tangent line is 0. And the slope of the tangent line is 0 if the derivative is equal to 0. So the numerator of my derivative would have to equal 0. It's already in a factored form. If I set the first factor equal to 0, I violate this condition directly. So I don't get anything from setting y equal to 0. But then setting cosine of x equal to 0, there is one location on the unit circle here that gives me a cosine answer of 0 that lies between 0 and pi, and that would be pi by 2. So x being pi by 2 makes the tangent line have a slope of 0, so it gives us a horizontal tangent line. But notice that it says find the coordinates of the point, not just the x value for that point. So we are going to have to plug pi by 2 back into the original equation, right? If I plug something into the equation of a curve and it satisfies it, that ordered pair will be appearing on the curve. So when I plug pi by 2 in for x, sine of pi by 2 is 1. So I get this equation here. And if I solve that by factoring, get my y over there to have it set equal to 0 and then factor it, I actually get two solutions to this. The solution here, when I would set this set of parentheses equal to 0, would give me y equals -3/2. But once again, we're only considering positive values for y. So I only get one point based on where y needs to sit, where I have a horizontal tangent. The x coordinate's pi by 2, and the y coordinate, set this equal to 0, y is going to equal 2. Final part of this says determine whether whether f has a maximum, a minimum, or neither at the point found in C. Justify your answer. Now, normally what we like to do when we're looking to identify or classify a location as a max or a min, we like to go with a sign chart for f prime. The difficulty in that is that this derivative is dependent on both x and y. So we're going to have to think a little more outside the box. We've used this a little bit, not as regularly as the first derivative test to classify local maxes and local mins. But if we know what the concavity of the curve is at a location where we have a horizontal tangent, we're going to be able to decide pretty quickly whether we have a max or a min at that spot. Now, concavity is going to depend on the second derivative, and what we're setting ourselves up to use here is actually called the second derivative test. When I take the derivative of both sides of this equation, the derivative on the left is nice, right? Just second derivative of y with respect to x. Derivative on the right is a mess because I have a quotient already and there is a product within that numerator. So what you see here is you see the function from the denominator of the expression, I should say, from the denominator of the fraction, and then the derivative of the numerator. What you see right here, I actually had to apply a product rule in order to get that into place, and then I'm subtracting off the original numerator and then times the derivative of the denominator, and that's all over the original denominator squared. Now, when I evaluate this at the point in question, which is the answer from part C, pi by 2 comma 2, what I end up with is I end up with quite a few instances of cosine of pi, which is kind of nice because cosine of pi by 2. Cosine of pi by 2 is 0, so all of those are going to go away. Now, sine of pi by 2 is 1, so those we don't get quite as lucky with. But if you simplify successfully here, what you should end up with is you should end up with a negative value for your second derivative at this ordered pair. And if the slope of the curve at this ordered pair is 0 and we have a negative second derivative, that means that we have a situation where we're concave down, and if we're concave down, we have to have a local maximum on the curve at this location, and the justification is the second derivative test.